today it's a pretty involved lecture, so we'll get stuck into it. There's some extra resources for this lecture if you need some other additional material, and it's a fairly big topic, and I'm going to go through some of the concepts reasonably quickly. Some of the examples that I would like to do in class, I can't really do in class because they need scripts, they need Excel to do all the number crunching. We can't do big matrix calculations on the board, so I'll skip through some of the concepts fairly quickly, but there's a lot of extra support material if you're trying to apply them on your own. So we've got Megson and the textbook, the Composites textbook is this composite material for aircraft structures, which there are some copies in the library, and I think you can get electronic copies of it legally as well through the library. And Engineering Mechanics of Composite Materials is a really good one as well. So there's also some other documents. That's an Amazon link if you want to buy the book, but you can look at that in the lecture notes. Okay. So first of all, the bit that everybody likes about composites is where they're being used. So if you've been paying any attention at all to the aerospace industry recently, you'll know that the big famous aircraft that are coming out by the two big manufacturers are moving more and more towards composites all the time. So the 787 was about 50% composite by weight, because as we know now, composites are significantly lighter than most alloys. So when we say 50% composite by weight, we're really talking about 80% of the volume of the aircraft was carbon fibre composite. And this is obviously a 787 up here, one of the nice renderings that Boeing likes to put on their website. They don't look that nice in reality, but yeah, once you put the ugly logos of different airlines on, they're not as nice. But this is one of the barrels after it's being machined. Okay, so this fuselage barrel here, I believe, is an aft section in the back of the barrel. Actually, it might be one of these four sections. I'm not exactly sure which section it is. Actually, you can see the wing box going through it there. So it's a wing box section. And this is a close-up of the inside of that section. So this is a carbon fibre skin here. So this is the skin, and these are carbon fibre stringers that are running up the length of the airframe. And this is a carbon fibre frame that's running around in the side of the shot here. So in the bigger shot, you can see the frames are running around like this, and the stringers are running along the length of the airframe. But the whole thing is carbon fibre, and they make that in one big piece. The frames are bolted on, as you can see, there's fasteners here, but the stringers and the skin are made in one operation. They actually put the whole thing into a jig, pump resin into the whole thing, and cure it as one big part. And then they machine out all the holes. Car enthusiasts would be aware of this car. I've actually seen this chassis in the flesh at a conference. This is a semi-monocoque composite chassis. Does anyone know the car? So, yeah, it's it. Yeah, it's a carbon fibre semi-monocoque chassis, and obviously it's got alloy parts to the rest of the chassis, but the centre part of the body is all carbon fibre, and no extra material in there at all. There's no alloy components in that central section. So obviously this is an area that not only aerospace manufacturers are going into, it's also automotive and sporting equipment, bikes. So anyone who's got a new racing bike, they're almost all carbon fibre. I mean, there are some very nice alloy ones around, but carbon fibre seems to be dominating that industry as well. Rail, so high-speed rail is almost exclusively carbon fibre composites or glass fibre composites now. So you can see that there must be some advantage to these materials, that they're starting to dominate so many market sectors, even people making silly composite things. There's actually a blog that places that composites don't belong, and this was a picture from the, from the blog. And so people are starting to make all sorts of things out of carbon fibre that shouldn't really be made out of carbon fibre. But you can see that there are a lot of there are a lot of uses, and it's got a lot of benefits, and we'll go through some of those benefits. But there are some complexities which we'll also have to deal with along the way. Okay, so first we're going to talk about design drivers and why specifically in the aerospace industry we've gone towards composite materials. So we've seen the top half of this plot before. In one of the early lectures I put this plot up with just the metals in. Now I've chucked some composites in the bottom. So you can see the things that are important to us, maybe the tensile ultimate strength and the modulus. You can see here if we've got carbon fibre down the bottom, we've got a tensile ultimate strength that's sort of on par with some of the steels, and a stiffness that is not quite as high as steel, but reasonably good. But if we look at the density column, you can see here, this number here, carbon density, is way, way, way lower than even aluminium. Okay, so we're talking about half the density of aluminium and significantly lower than steel. So once we take the structural efficiency, which is the strengths divided by the density, we're looking at huge benefits of carbon fibre over even steel or aluminium. We've got really, really big numbers here. So purely from a structural efficiency perspective, so a strength to weight ratio or stiffness to weight ratio perspective, carbon fibre is a really, really good material. And Kevlar was also pretty good, and fiberglass is not quite as good, but still reasonably high. And we'll talk about why Kevlar is not necessarily used as much as carbon in a minute, but glass fibre primarily doesn't get used too much because it's got the same complications as carbon fibre, but it doesn't have the same benefits. So it tends to only get used in certain applications. One of those applications is anywhere where there needs to be no conductivity. So if you need to have a situation where you can have radar transmit through a particular piece of structure, for instance the domes at the front of the aircraft where they have a lot of communications equipment, that's generally made out of glass fibre because carbon fibre is conductive. So you create a Faraday cage that, just like having a metal plate there, the radar can't get through it. So you can put a glass fibre radome on the front. But there aren't many places that glass fibre gets used. Okay, so on top of the weight reduction, there's a lot of other reasons that we would go to composites. Weight reduction actually turns out, once you account for some of the complexities of carbon fibre, the weight reduction is not quite as attractive as it is by looking at the numbers in that last table. There are a lot of other things that really push the market towards composites. One of them is improved performance, so making better aerodynamic shape. So anyone knows who's interested in aerodynamics would know about supercritical airfoils and special airfoil profiles. There are a lot of advantages to being able to push closer and closer to Mach 1. Obviously your aircraft's going faster, so you're getting from point to point faster. But if you can reduce the huge drag overheads that come with those increased speeds by using special airfoils, then you can make a lot more money with your aircraft. In order to do that, it's very hard to make some of those airfoils out of aluminium because they just they're hard to form into the right shapes, whereas composite you can form into very precise shapes. Reduced acquisition costs. So when I said a couple of slides ago that this whole aircraft here, this whole piece of the aircraft is made in one part, okay, this is one manufacturing operation for the majority of the fuselage barrel. So you can save a significant amount of money on, even though the raw materials are more expensive, you can, if the numbers are right, if you balance your production correctly, save a lot of money because you're not having to go along with an alloy stringer. You've got to put a fastener every inch or so. You've got hundreds of thousands of fasteners, lots of different manufacturing operations. The cost to actually manufacture that section out of composite can be significantly lower because they can reduce the number of manufacturing operations significantly. And the last one, which is a really big one, and it's probably all said and done the one that's really driving the industry towards composites, is reduced through life support costs. Composites are significantly better at resisting fatigue than alloys are, and they're significantly better at resisting corrosion than alloys are. So over their life, they need less inspection and less effort going into maintenance and repair. And if you've seen how much money airlines spend on maintenance, then this is a really, really big benefit of a composite aircraft. Okay, so this is old data. I don't have up-to-date data for this. This is from about 1990, but the ratios would be about the same now. The dollar values might have gone up. This is the approximate saving for the lifetime of one aircraft if you could save a kilogram of weight. So if you could, by some redesign effort, take a kilogram out of the aircraft weight, this is how much over the life it would save in operation. So obviously for the space shuttle, you take a kilogram out, you're saving a lot of money, but for smaller aircraft, it's not as much as you'd think. And the reason that we're seeing composites at this end of the market as opposed to this end of the market is purely for that dollar reason, that if it's a lot of effort to redesign parts to be made out of composites. You need new manufacturing equipment, new tooling, new skills. So you only will make that weight saving if there's the payoff in return for doing so. There's not the money in redesigning a Cessna to be made out of carbon fibre, but there is the money in redesigning an airliner to be made out of carbon fibre. And I was mentioning before about maintenance effort. This is some data from American Airlines, and they do 5 different levels of checks. So they have what they call pre-flight checks, which are these lots of blue ones. So on the left we've got frequency, on the right we've got total hours. So you can see they do a lot of pre-flight checks. Obviously every flight there's some checking. Then there's A checks, B checks, light C and heavy C checks. Now the amount of time in total, not just per check, the amount of time in total that they spend in person hours is on the right. You can see that one of these heavy C checks, even though they might only do it for every 18 months or even longer in some cases, every 3 years, 5 years for an airframe, you're talking about a really, really, really long period of time in person hours. And the total time for 1 hour of flight for an airframe owned by American Airlines, there's 11 person hours of maintenance goes into the aircraft. So you're thinking each day an aircraft's flying, if it's a short haul aircraft, it might be flying 15, 16 hours a day. If it's a long haul aircraft, it could be flying anywhere up to 20 hours a day. And they're putting in 11 person hours per flight hour for every single aircraft in their fleet. So if you can save a bit of that effort, there's big margins there to be made if you can reduce that maintenance effort. Okay, so that's the reason we would go to composites, and now we'll start talking a bit about what a composite is and how we make a composite. So the basic definition, the one that if someone asks you to define what a composite is, it's a combination of 2 or more materials with distinctly different physical properties. Okay, so when you put 2 things together, in the case that we'll talk about most commonly, that's fibre and resin. But there are a lot of composites around. They don't have to be these modern man-made composites that we're talking about. Wood, for instance, hardwood is a composite, or any wood is a composite. There's a stiff cell structure, and then there's a matrix around it which bonds it all together, and that forms a composite material. The combination of constituents leads to a new material with characteristics unlike either of the constituents or any of the constituents. And one thing that distinguishes a composite from, say, an alloy is that the two constituents remain separate and distinct. So when we make an alloy, we get some aluminium, we get some magnesium, some zinc, and whatever, and we mix it all together and we make an alloy. That is not a composite because the different constituents are all mingled together. They're forming the same crystalline structures and forming the same phases, whereas in composites, those two things remain distinct. And useful composites, composites that we would actually bother with, have properties that are what I'd say greater than the sum of their parts. You get some advantage by putting these two things together that you wouldn't have gained from using either of the materials independently. And that goes as far back in human history as putting straw into mud to make mud bricks, because the straw has some strength to it that the mud didn't have, and so you can make your housing out of it. But composites have got a long history, but we're only using them in aircraft fairly recently. So to categorise composites, the kind of composites that we are interested in are generally unidirectional composites and fabric composites, but we can categorise them in different ways. So some of the simplest composites just have a particulate filler. So we have to have some form of matrix or binder that holds everything together. That binder can be a polymer, it can be a ceramic, it can be a metal, it can be anything really. The ones we'll talk about most are polymer. But then we put something in it that's got different properties. So we can put particles, so zero-dimensional things, points. We can put these one-dimensional short fibres that are either aligned or random, or we can have continuous fibres. And the ones with the best properties are these continuous fibre composites, because obviously if you've got short fibres, they've got lots of stress concentrations everywhere. You've got load coming into the fibres, load going out of the fibres, and there's lots of places for them to fail, whereas continuous fibres have many fewer stress concentrations. So, as I've said, the fibre reinforced composites are most important for us, and the way we make them is we have a stiff and strong fibre, so a fibre that's got very, very good properties in one direction, and that's the only direction we really care about, because across the fibre is very, very hard to load or measure what the properties are. Carbon fibre is, which as we'll see in a minute, is about 7 microns in diameter, so it's a very, very fine fibre. And then we bind it into something that's more flexible and significantly weaker, but cheaper, malleable, formable, so we put it in what we call a matrix. And I will use the words resin and matrix fairly interchangeably. And one of the problems with our discussions today about composites is that there's two different uses of the word matrix, and I'll just try and explain. There's matrix in the mathematical sense of a matrice or matrix, but there's matrix in the composite sense, in the material sense, is a material that binds all the fibres together. So you just have to be a bit careful that you understand when I'm using one or the other. Okay, so that's a carbon fibre here next to a human hair. So you can see they're fairly fine, but very, very strong materials. They approximately 7 microns in diameter for most carbon fibres. It varies a bit depending on the manufacturing process, but they're very, very small. They come in what we call rovings or toes that are of a certain number of thousands. So they're generally written something like 3K or 6K, which stands for 3,000 or 6,000. So they come in little bundles of, say, 6,000 fibres. And we can weave that into a sheet, if necessary, into a fabric, or we can pre-impregnate it with resin and make flat sheets out of it. There's lots of different processing techniques, but effectively fibre starts off in this way, in this form, and then gets turned into something else. And we tend to add to that for aerospace applications a polymer binder, so a polymer matrix. And there's two broad categories. There's thermosets and thermoplastics. So thermosets, I'm not sure about your chemistry or your materials background, but thermoset polymers are polymers that go hard via a chemical reaction, so that you have two liquid phase constituents go in and there's a chemical reaction and they set hard and there's cross-linking, whereas thermoplastics go hard via physical reaction. They start as a solid material, you melt them, so they become liquid when they're molten, and then they cool again and go hard again. So thermoplastics are a phase change, whereas thermosets are a chemical reaction. Now I'll just define a few terms before we go any further. Isotropic, anisotropic and orthotropic, they all sound fairly similar, but they mean quite different things. Isotropic materials are what we're used to. So isotropic materials, any alloy is effectively isotropic unless you roll it in a particular direction. But a plastic or a metal by default is an isotropic material, and it means that it's the same in any direction. If we took a piece of it and cut a specimen out one way or cut a specimen out the other way and we tested their strength, they'd be the same. There's no change in strength or properties depending on which way we look at the material. Anisotropic materials do change. And so one of the anisotropic materials that you might be familiar with is if you take a piece of metal and you cold roll it, so you roll it into a big flat sheet, all the crystals in the metal go from roughly spherical to big long flat sheets. And when you do that, they get much higher properties one way than they do the other way. So that rolling process creates an anisotropic material. And it's, you can imagine a carbon fibre or a composite made of carbon fibres is an anisotropic material because it'll have different properties when we load the fibres than when we load the resin that's holding it together. And orthotropic, which is a common term in composites, is a special case of anisotropic. It's a special case when there's three mutually independent axes. So there's three ways of looking at the material that are independent of one another. So Cartesian coordinate system generally. So if you think of X, Y, Z, if those three directions are independent in the material, we call that material orthotropic. And we'll see a little bit more later on about how that pertains to composites. Now if we flick back into our units that we're a bit more familiar with, so our SI units, we've got carbon fibre stiffness and strength there. This is just the fibre itself. This is not the composite, so we have to be a bit careful. That previous table I showed you was the composite properties. Now we've just got the fibre properties. So carbon fibre properties and epoxy resin. So stiffness for a carbon fibre from an epoxy is about 100 times the modulus, and the strength is about 200 times, or maybe not, maybe 100 times. So we're posed with a question, why would we use a composite at all? Why not just make a structure out of fibres? So why do we have to make a composite? Why do we have to add this weak epoxy material in? Yeah, so it's effectively to make a component. You can imagine if you made something out of fibres alone, it would be just like a fabric. Your clothes are just fibres. They're a woven type of fibre. They're very, very, very strong if we load them in tension or in shear. But if you load them in compression, or if you start poking holes in them or scratching them, they become quite weak. You can cut through the fibres in your clothes quite easily. So what the resin does is it actually makes it into a structural material that we can use. It protects the fibres from the environment, holds them together. It distributes load between them. And it does determine some of the properties of the composite. So the compressive strength, as I've said, the tensile strength is generally defined by the fibre. So if you take a piece of cloth and you pull on it, you'll be loading fibres. But the compressive strength is a combination of the fibre properties and the resin properties. And a lot of other things which we'll talk about in a minute. Fracture toughness, operating temperature, fire behaviour and corrosion resistance are all determined by the matrix. So the fibres themselves, although they're very, very strong, very flimsy, you can't load them very easily. So the matrix is really distributing the load between the fibres and helping with the overall strength. So the simplest composite that we can really imagine, simplest fibre composite is this one. So it's, I've drawn the fibres very big there, but in reality you can't really see the fibres when you look at a composite because they're so small. But we've taken a bunch of fibres and we've loaded them, put resin around them. So we've made a bar specimen and put a bunch of fibres in. And in practice, when we do this, we get somewhere around 60 to 65% of the total volume of the bar is fibres. Okay. Can anyone think about what the maximum amount of fibre you could get in would be? And how you'd possibly work that out? Okay, these fibres are roughly cylindrical. Well, if we think about how if you put ping pong balls in a container, they can't fill the container because they're spheres, there's gaps between them, and you can work out the most efficient way of packing balls into a container. It turns out that atoms in a metallic lattice are often packed in the most efficient form that they can be. Now, the way you can work out how densely packed you can pack fibres in is to imagine that they're packed in a hexagonal shape. They're cylinders, so they're coming out of the board as tubes. But it turns out that the maximum is about 91%. In reality, we don't get near that because you start getting detrimental effects when you go too high. We generally go about 60 to 65% fibres. Now this would have great properties if we just loaded it in that direction, because we'd be loading primarily the fibres and everything would be fantastic. We would get really high structural efficiencies. We'd be able to get an astonishingly strong material if we did just that. But the problem is we never know the load well enough, and the load's never perfect and aligned like that. And if the load is in the other direction, then our composite is very weak. Remember that the fibre properties were about 100 times the strength of the resin. So if we instead loaded it this way, we'd have a material that would drop in strength by a factor of 100. So in practice, we have to make what are called laminates, where we stack the fibres in different directions in order to get a strength that's reasonable in all directions, and we'll talk a bit more about that in a minute. Now, we tend to determine failure of composites based on strain, and we'll talk about that at the end of the lecture, but carbon fibres roughly can take about 1% strain before they fail. So they're fairly brittle, linear materials. So if you think about polymers, high density polyethylene, that might take tens of % of strain before it fails. It can stretch quite a long way before it fails, whereas carbon fibres are about 1% change in length. So if you take fibre that's a metre, you might be able to stretch it, 10 10 millimeters before it breaks. Okay. Glass fibre is about 2%, aramid fibre is about 2%. Whereas the resin that we put in, the resin might fail at 5%, 10% strain. So we've got a very ductile material that we're putting around very stiff fibres. Okay. When we stack these plies, so that if someone said, okay, I've got going to load my composite this way, but I'm also going to have some load in the other direction, you would say, okay, I'll come in and on my next layer, so this might be one sheet of material. The composite tends to come as sheets. So these thin sheets that are maybe 0.1 to 0.125 millimeters thick. If they're a fabric, maybe 1/4 of a millimeter thick, but they're very thin. So you'd get one sheet and you'd stack it that way. Then if someone said, oh, well, we've got some load in the other direction, you might come and stack a sheet that way so that you carry that load. And if someone said there was some shear, you might come and stack some at 45 degrees and plus and minus 45 degrees to take those loads. So you can really build up a composite to carry whatever loads you want it to carry. So you can tailor it. And the key benefit of design with composites is that you can tailor it specifically for the loads that it's going to experience. So if you have a good enough knowledge of the spectrum of loads that a component is going to see in its lifetime, you can stack the plies exactly to match that set of loads rather than having a material like a metal where it's strong in all directions even though it may not need to be. You can really tailor the composite to be strong only in the directions that it needs to be, and hence saving weight. So as just a summary of the properties of composites before we move on to a bit of analysis, we've got an advantage of composites over, say, alloys. Decrease in density, which we've seen before, increase in material properties, so specific strength and specific stiffness, very good fatigue life, good corrosion resistance, damage tolerance. The big one here is tailorable anisotropy, so we can actually make it exactly how we want it to be for the particular application. But on the other side, the material itself, the raw material, is significantly more expensive, so we have to recoup the raw material cost by having better fabrication techniques. For very big production runs or very large structures like an airliner, that's easy to do. For smaller structures, it's not as easy to do. One thing that is changing, and I've got here low automation, this is something that's really changing in the industry. It's probably the biggest thing that's changing in the composites industry at the moment is the amount of automation. So it used to be that when you made a component out of carbon fibre, you had to actually manually, by hand, lay the sheets of material down into a mould as you're making it. So if you can imagine making, say, the tail plane, or even an elevator for something like a 777, which is something I've seen being made. An elevator for a 777 is many metres long and many metres wide, and you've got to get a big sheet. If you've ever stuck something like contact onto an exercise book, these materials, when you make a airliner out of them, are often what we call pre-impregnated with resin, so they're a bit sticky so that they can stick them into the mould. You've got to position a piece that's many metres across very accurately into a mould without it getting stuck and trying to pull it up and rearrange it. So you've got people on gantries and swinging from harnesses from the roof to try and get this position in a mould. So it was a very, very labour-intensive process to build composites. That's changing. We're starting to get robotic solutions now that are going into the market where they're actually getting big robots to lay the material into the mould for them. And we actually in the school, as of very early next year, are going to have a robot to make composites as well. We got some grant money for the government to buy one, so we're going to have a robotic composite manufacturing facility from somewhere around February next year, hopefully. So you guys are probably going to get to see it in action. Quality control is a big thing for composites. So because it's what we call additive manufacture rather than subtractive manufacture. When you make a metallic component, generally you start with a big piece of material and you cut out the bits you don't want. And the big piece of material is made in a factory in such a way that its quality is checked fairly precisely when it's made, a rolled sheet or a billet of material. You can be assured that the quality is pretty good. Whereas with composites, it's additive manufacture. You start with nothing and you put the material just where you want it. But because you're putting material into a mold, you've got to be very careful that other bits don't get in there with it. You don't get grease and things that are going to detract from the quality of the part. You don't get dust and inclusions. So the quality control requirements are very high. You need very precisely controlled humidity rooms, precisely controlled temperature, clean rooms, all sorts of things. So the quality control becomes a much, much harder thing to manage. You can drill a hole in a piece of aluminium in the dirtiest, grimiest place you want, and you'll still have a good piece of aluminium there. If you try and make a composite in that kind of condition, your quality of your part will be rubbish. One other thing which it's sort of at the back of here, lightning damage is a bit of an issue for composites. They are solving that a little bit, but composites are conductive, but only the fibres are. The resin generally isn't. So you have this situation where if you do get a lightning strike, you've got these little fibres that are very conductive because carbon is highly conductive, but between the fibres it's not so much. So the current tends to run along the length of a fibre until it runs into the end of the fibre or something else, and the end of the fibre tends to be at things like bolt holes, and so you end up with a little spark gap between the end of the carbon fibres and the bolt, and you can get explosive damage around fasteners, which is not exactly a good thing for maintaining the aircraft in one piece. So they've solved that by putting copper meshes in aircraft when they make them out of carbon fibre. They've got a very, very fine copper mesh between some of the layers that they put in, and that makes the structure much more conductive and can dissipate those lightning strike problems. And one last one which we talked a bit about with NDI, but damage can be difficult to detect. So the types of damage that you experience in composites is different to the type of damage you experience in metals, and sometimes it can be trapped inside and you can't see it very easily. So you have to come up with techniques to capture that kind of damage. We've talked a lot about the constituents that make up carbon fibre composites, or any composite, and we've talked about the properties that those materials have and what the advantages of them are over other materials. But when we come to the stage of actually applying these materials, we really need to have some way of predicting what their properties are going to be, because there's a lot more variables with composites than there are with metals. With a metal, your properties are really determined by the alloying components you put in, maybe some heat treatment, but with composites you've got a lot of variables. You've got the fibre type you've chosen, the matrix type you've chosen, the relative proportions of fibre and matrix, how the laminate is stacked. There's lots and lots and lots of variables there, and so to design with them you need to be able to go from a simple set of properties to a more complex set of properties using some analytical techniques or simulation techniques, but we'll start with some simple predictive methods. So the first some definitions. We'll have some different volume and weight ratios here that we'll talk about. So fibre volume ratio is the one that we will talk about most commonly, and what I will use, if I say volume fraction, I mean fibre volume ratio. So volume fraction it's the percentage of fibres in the total composite. So a volume fraction of 0.6 means there's 60% fibre and 40% resin, roughly. Now, we don't tend to use weight ratios as much because they affect the properties less. But when you're making a composite, the weight ratio is relatively important because you tend to weigh fibre and resin. You don't tend to measure volumes. You put them on the scales. You say, I've put a kilogram of resin with 5 kilograms of fibre or something to that end. So the weight ratio is most important when you're making them, but the volume ratio is more important when you're determining the properties. There are some other ones down the bottom here. This void volume ratio used to be a bit of an issue, but it's probably not as much anymore now that our manufacturing's got better. We tend to, with aerospace composites, have a void fraction of less than 1%. It tends to be the gold standard for a good quality composite. So we can almost forget voids, but you can imagine that if you're pumping a liquid material into fibres, then occasionally there might be gaps. There might be bubbles or voids in there, which is not contributing to the properties at all. All it's doing is taking up space. But with composites, as I said, with aerospace applications, we aim for less than 1%. So this is really not much of an issue. We can sort of almost neglect it from an engineering standpoint. So when I talk about volume fraction, I mean this fibre volume. So if I say fibre volume fraction of 60%, you can immediately assume I mean a matrix volume fraction of 40%. Now, because the fibres we're concerned about are cylindrical and continuous, if I was to take a slice through any part of the material, I would see a bunch of circular fibres, and they are actually quite circular for most carbon fibres. Some types of carbon fibres aren't quite circular, but okay. And obviously, depending on where I'm looking in the microscope, I can have fibres sort of hanging over the edge too. Okay, so if I've cut through my specimen and I can see these fibres, obviously the circular bits are the fibres and the rest of it's matrix around. If I told you that the volume fraction of fibres was 60%, what fraction of area on this slice would be fibre? 60%, yeah. So the area fraction and the volume fraction are the same thing. So we tend to, when we measure these quantities, we tend to measure them with a microscope. We actually take a specimen, cut it, polish it, and measure the area percentage of fibre and matrix. The other way to do it is to do it by weight and using densities, but depending on the type of property you're after, the area fraction is also interesting, because area fraction is the one that determines our properties most, because all of the things we're interested in, like stiffnesses and strengths, are force per unit area. We're used to megapascals and gigapascals. We're talking about a particular force acting on a particular area. So area fraction is the thing that really determines what our mechanical properties are going to be. Okay, so the simplest way we can predict what the properties are going to be is with what we call a rule of mixtures. And don't get too lost in the formulae. We'll just look at the first one at the moment. So just focus up here. So if we had our example before, and for the next little while we're only going to talk about single plies, what we call lamina, so just one layer of material. So if this was our lamina with our fibres in it running from left to right, we tend to set up a coordinate system that looks like 1, 2. So 1 means in the fibre direction. 2 means across the fibres, but in the same plane as our sheet of material. And 3, if we define it, is the through thickness direction. So 3 doesn't come into our calculations that much, except if you're using complicated failure criteria later on. But most of our calculation for composites can be done in a plane stress environment. So just like when we did our metal calculations last week, we looked at an element of material and we're really only considering sigma 1 and sigma 2. We generally, with composites, are really only concerned with the in-plane properties as well. So that top left formula is the simplest rule of mixture formula, and it says if we wanted to work out the modulus of this material, this new composite that we've made, how could we do it? Now, how do you measure stiffness in reality? We talked about this last week. How do you, if I made this composite and I didn't know what it was made from, how would I test its stiffness? We apply a load to it and we measure the change in length. Okay. And we apply a load, measure a change in length. We get strain from the change in length over the initial length. We get stress from the force over the area. And we get modulus from stress over strain. So in practice, what we can do, if we know the fibre properties and the resin properties, we can work out what we call engineering properties for the composite. So in this case, we don't have to know whether this is steel, composite, aluminium. That doesn't matter. The process is still the same. If we were measuring the modulus, we would still measure it this way. Now, to do that, I've got E subscript 1, which means the modulus in the one direction. And as I've said, these materials are anisotropic, so they're going to have a different modulus that way than they do that way. So the subscript means the direction that we're looking at. So E subscript 1 is equal to the modulus of the fibre. So E for the fibre, what we said was approximately 200 gigapascals before. And what did we say the E for the matrix was? About 20. Actually, modulus is probably lower than that. It's probably more like 2 gigapascals. The strength is about 20 megapascals. So about 2 gigapascals. So we had E1 equals the modulus of the fibre times the area fraction of the fibre. So that, remember I said that if we cut a plane through our material, it's the area of material that really matters, plus the modulus of the matrix times the area fraction of the matrix. Now, because these are continuous, we can switch area fraction for volume fraction. And we know, because we're assuming that there's no voids, that the volume fraction of the matrix is 1 minus the volume fraction of the fibre. So we can rearrange again. Okay, and this is our simplest rule of mixtures formula for the axial stiffness of the composite. And for a lot of simple design with composites, that's about as much as you need. We can build up a lot of the properties of the composite using just that. I will go through the other ones as well because they are important for some applications, but you can get a long way down the path using just that formula. Now, let's just think about this for a second. I've told you that the fibre volume fractions are somewhere between 1/2 and 1 generally, 60%, 50%, depending on what we're trying to do. So that means that the magnitude of this term and the magnitude of this term are about the same. There's not a huge variation between the size of these two terms, but there's a massive variation between the size of these two terms. So the volume fraction of the fibre is, the modulus of the fibre is much, much higher than the modulus of the resin. So in practice, we can, for the kinds of composites that we're interested in, this nearly goes to 0. It doesn't quite, but it's fairly insignificant. We said here that the fibre was 200 gigapascals and the matrix was 2 gigapascals. So if you've got 200 times 60% plus 2 times 40%, the 2 times 40% just sort of disappears into the error of your calculation. So a rough and ready formula that tends to work pretty well is actually just that. Okay. Now the other properties that we need, and we don't need them as much. The E1 is the driving force for most of our composites design, but we do need some of the other properties in some cases. The other properties are the modulus in the 2 direction, which is E2. And the reason that the formula there is a bit more complicated is because instead of loading the fibres and resin in parallel, if you imagine we're loading here, there's fibres and resin both being kind of loaded at the same time. If we load in the 2 direction, we're really loading them in what I'd call series. Even though it's not as simple as resin, fibre, resin, fibre, resin, fibre, we're really, some of the load's going into the resin and then it's going into the fibre and then it's going into the resin and then it's going into the fibre. And it turns out that that means that much like resistor calculations where there's a different formula in parallel and in series for resistance, there's a different formula in parallel or series for working out the rule of mixtures. So the modulus in the 2 direction is significantly lower, and it turns out that if we look at this formula, so in this case, remember we said that these terms are about the same, but there's a big difference between these terms. The fibre modulus is much, much higher than the resin modulus. So this term, in this case, can be considered going to 0. So our rough and ready approximation here is that it's the matrix modulus over 1 minus the volume fraction. So in our composite we've got up the top there, in the fibre direction everything's going to be very stiff because it's driven by the fibre properties. In the transverse direction everything's going to be very compliant because it's driven by the matrix properties. And you can get progressively more complicated with your approximations depending on how accurate you need to be. So never go too far into this unless you need that accuracy for your calculation. And for most calculations, as we'll see, that the accuracy just isn't that necessary. Now, shear modulus, G12, okay, just like an isotropic material has E, G, and nu that are the Young's modulus, shear modulus, and Poisson's ratio. There are also some other ones, K and lambda, and some other numbers that are all related. But with an isotropic material, you really need two of these to define the problem. So if you've got E and you've got G, you can work out nu. Or if you've got E and you've got nu, you can work out G. Whereas with composites, you need all three defined independently because they're anisotropic. So G has its separate formula. We can't go from E and nu to G. We have to work that out separately. And this is the formula for it. But as I've said, in most cases, the shear modulus is not super important for our calculations. And Poisson's ratio as well. So most of this you'll only be using as reference, but I will do an example. Okay, so let's do an example quickly. So because composites are highly tailorable, it becomes quite tricky to tell someone what kind of composite you mean when you talk to someone about a composite. So there's a series of codes that we build up to determine what we actually mean by when we specify a composite. So if you were to specify someone was making an aluminium aircraft, you would say, I want it to be made from aluminium. Then you would give them a code like 2024, which tells them the alloy components that were in the aluminium. Then you would tell them T3 or T4, which tells them the type of heat treatment. So when you specify a metal, you're giving them a form of code. When you specify a composite, there's a similar sort of code. We generally write the fibre type first. So in this problem, it's T300, and that's a particular type of fibre that's made by Toray. Okay, the T stands for Toray, but it's an intermediate modulus fibre. And then we put a slash and then put the name of the resin. So in this case, the resin code is 913. And depending on the resin manufacturer, they have different codes. But this resin's made by Fibre. But the most resins you'll see floating around on data sheets for aerospace applications are made by Hexel. Toray has products. The other one, another big resin manufacturer is Sycom. Okay, so after you've been in the composites, if you've been looking at composites for a while, you'll start to recognize these names popping up and up again. But we'll see that this is the beginning of the code. So if I was to specify someone aluminium, it's the equivalent of giving them this. I've told them the materials that have gone in, but I haven't told them anything else yet. So this is just the beginning of the code, and we'll see in a little bit how we make that code a little bit more complicated. So we've got our T300 913 composite, and we're going to make it from we need to work out its properties. So we've got its matrix modulus here of 3.39 gigapascals, fibre modulus of 230 gigapascals, and volume fraction of 0.64. Now we've got some measured data, but we want to see how good our predictions are compared to the measured data. So what we've been asked to do is work out the two moduli, and we'll work out the Poisson's ratio as well. So we'll work out E1, E2, and U12. Just as an intro here, we'll see why in a minute, but with these materials, the subscript order matters. So nu12 does not equal nu21. 147? Okay. I won't get too crazy with significant figures. 9.5? And the Poisson's ratio, I'm not sure we were given enough information to calculate the Poisson's ratio. No, we weren't. We weren't given any Poisson's ratio, so don't worry about that one. Okay, so you can see that the predictions aren't too far off. There's some reasons why they might be good or bad, but we'll see that depending on generally the 1-1 prediction or the 1 prediction is pretty good, and the 2 predictions not so great, but in this case they're both reasonably good predictions. Now I'll leave this example for you to do on your own time. This is a glass fibre, so I've got G stands for glass, so glass fibre reinforced plastic. And you can do this one after class, but you can see the ratio between the moduli is not as big. So the glass fibre, the fibres and the matrix are much closer to each other. I've actually written it incorrectly there. It should be big VF for most of these cases, or little v. I know it's tricky to see in the fonts, but generally V or big V or little v is volume fraction, and U is Poisson's ratio. But I think I've used a different font set. This has changed fonts and it's gone to a new. But that should be a little VF there instead of a new F. I don't know whether that's actually a new or it's just a dodgy font. But
so is there an actual difference between the two?
No, those are both volume fraction, and you'll see them used interchangeably depending on the textbook you look at. Nu is Poisson's ratio. This is different. This is a material. This is the ratio between the strain in the one direction and the strain in the two direction.
Because like I'm looking at the online notes, and you've got Poisson's ratio equaling little VF times big VF.
This one here. Yeah, see, that one there is meant to be a nu, and that one's a V. That one's a nu, and that one's a V. So unfortunately, that's the notation that textbooks use, including Megson, so I stuck with it. But the curly ones are nus. In some textbooks, you'll actually see, probably to resolve this particular confusion, some textbooks you'll see mu instead of nu for Poisson's ratio. So if you see, they've probably, to save this confusion, they've switched to a different character. But just, again, you've got to be careful. But in this case, we're trying to calculate Poisson's ratio. So we've got a Poisson's ratio times a fraction, Poisson's ratio times a fraction. So. Okay. So we've looked at predicting the elasticity in one direction, but we know these materials are anisotropic, and the way we've done them at the moment, they're orthotropic too, because the three axes are independent of one another. When we make a laminate doesn't have to be orthotropic, but in this case, because we've only got a one-directional lamina, it is guaranteed to be orthotropic. So the stress that we can apply to that, if we're just considering the plane stress that we can apply a one-direction stress, we can apply a two-direction stress, or we can apply a shear stress. And the reason I've got 6 as a subscript to that is a bit of historical background to that. But remember last week we learned that stress is a tensor. Okay, so the way that people tend to write it with composites is like that. And because we've got a plane stress condition, those 3 disappear. And so we're only left with direct stress 1, direct stress 2, and shear stress 6. So if you see a 6 as a subscript, just be aware that it means in the shear direction. Okay, I'm not sure how much detail to go into with these next slides because some of them get fairly mathematical and the maths is not something I can give an example of in the class. So if the pace is going too quickly, let me know and I'll slow up. So just like we can measure elasticity measure the stiffness of metals, we can measure it for composites, and we did an example of that a minute ago. So we worked out what the 1 modulus was based on the extension of our bar that I've actually just rubbed off. Now, last week we made the stiffness and compliance matrices for an isotropic material. Now we're going to do it for an anisotropic material. So if we apply a load in the one direction, we get a strain in the one direction, but we also get a strain in the two direction. And this is where the difference between U12 and U21 becomes important. When I write U12, I mean the strain that I get in the two direction over the strain I get in the one direction. So you can think about that if this is 1 and that's 2, the amount that I pull it in the one direction, the amount that it shrinks in the two direction gives me this order. Okay. U21 equals the opposite. We'll see in a little while that they're related to one another, that we can have a formula that links them, but we have to be just aware that those things are different. So just like last week, when we want to work out the full elasticity matrix or the stiffness matrix for this material, we have to apply strains in one direction, strains in the two direction, or measure strains based on stresses. Here we apply stress in the two direction and measure strains. We can combine them into a matrix like we did last week. So at the top there you see the same matrix that we developed for our material last week, except there's a few more subscripts in there. I've taken out strain 3 because it's not important at the moment. So we've just got strain 1, strain 2 and gamma 6, stress 1, stress 2 and shear stress 6. So this, apart from the subscripts, is you should be familiar with from last week. When we're using composites, we tend to give these, rather than writing these in a clunky form, we give them another symbol, because instead of, if we want stress on the right and strain on the left, we can use this. But if we want stress on the left and strain on the right, which is generally the way we write this, we need to do some rearrangement. These things get clunky to write over and over and over again. So we make a substitution, Q11. Okay, that means this is what we call a reduced stiffness coefficient. And it's exactly what it means. It's exactly what the name says. It's a stiffness coefficient, so it's a coefficient in the stiffness matrix, and it's reduced in the sense that we're not writing out the full term. We're just using a symbol for it. And these are the formulae for the reduced stiffness coefficient. So this is, apart from the subscripts, this is still no different from last week. We've used a couple of different symbols, but this slots in directly after what we learnt from solid mechanics last week. So let's calculate some of these reduced stiffness coefficients as an example. And here we have a Hexcel T300 5208 composite. And I'm sorry if you can't read that data from the back, but the data that we're looking at is in the orange box across here. Okay, so this is a data sheet from online. Okay, so we've got to work out the reduced stiffness coefficients, the four that are shown there, Q11, Q22, Q12 and Q66. And again, the 6, this 6 refers to the shear direction. And again, I've actually quickly skipped through something that's generally quite confusing for people. These things are exactly equivalent. If you see E11 or E1, they mean the same thing. It just depends on the notation in the textbook. So I bagged this one. That one I can do myself. The rest I wouldn't be able to do accurately in my head. Okay, so the way we can calculate nu21, okay, let's work this out here. So Q12, you see has got two different formulations for it there. Okay, so we know that the bottom here is the same. So the top has to be the same. So we can say nu21 E1 equals nu12 E2. Okay, so nu21 equals nu12 E2 over E1. Okay, so this is the formula that links nu21 and nu12. So this is big and this is small. So nu21 should end up being smaller than nu12. It also means you can make that substitution if you want. You can substitute in nu21 into the bottom half of your formulae and make that substitution, and it means that you don't have to handle nu21 everywhere. But what you should be seeing by now, if you've got any answers coming out, for this particular case, for carbon fibre, that bit on the bottom ends up being pretty small, because this is something like 0.3. When you square 0.3, you get to 0.09, so this is like 10%. And then here you've got E2 over E1, which is about 1%. So, or maybe a bit more than that, 10% say. So you've got 10% times 10%, that's about 1%. So on the bottom, you've really got something that's about 0.99 or something that this term really doesn't, for this particular composite, doesn't add up to much. For most carbon fibre, that term is pretty small. So I'd be pretty reasonable in guessing this is going to be about like 182.5 or something like that. It's not going to be far off 181. May not even be that high. This one might be like 10.5. 181.8. 180. Okay, so it hasn't gone up by much. So really, if we're only manipulating the 4th decimal place, we really haven't done much here. Q12 will have a different value though. We have to calculate Q12 because Q12 has something interesting on the top that's not one of our initial properties. It'll be something like 3 gigapascal, I think. 2.9? What was this one? More 10.4 or something like that? Okay. Okay, so you can see for this particular problem, that was a bit of a waste of time because they were very similar, but I can assure you in the general case that's not always as easy to do. Most of the time for carbon fibre, because the fibres are so much stiffer than the resin, we can, most of these formulae simplify very quickly. So if you know your fibre and your resin are very different in stiffnesses, you can pretty much get rid of everything that's on the bottom And the only one you've actually got to put any maths into is the Q12. Now, just when I've told you it's all really easy, I'm going to throw a big spanner in the works. Okay, and start throwing matrices around. And this is why I said I can't do the maths in the class, because I can't crunch matrix calculations on the board. But we don't always apply our composite in one of the nice axes, like the 1-axis or the 2-axis. When we make a laminate, we have to put them at different orientations. So we need to be able to calculate the properties in those different orientations. And we can do, just like we do Moore's circle, we can do the equivalent of Moore's circle with an orthotropic material. And it turns out that this maths that I'm showing you here is actually just a generalized form of Moore's circle that you wouldn't have been aware of, because second year teachers are too worried about introducing matrices. But we can do what's called a transformation on the vector, and we use this transformation matrix, and all the terms in that transformation matrix are all derived from cosine theta and sine theta down here. So m is cos theta, n is sine theta. We create a matrix that's m squareds and n squareds, and we can rotate one stress state into another stress state just using that rotation matrix. And one of the beautiful things about this matrix is that to get the inverse of it, all you have to do is put in minus theta. So you don't actually have to do an inverse operation. It's set up in such a way, quite cleverly, that instead of doing an inverse, which you'd have to do to switch, if you wanted to switch these two around, you'd have to calculate an inverse. All that equates to is rotating through the opposite angle. So it's a very easy rotation to do, or a translation to do. Now again, you'll notice there's this half floating around. Remember I said that engineering shear strain, you often have to make the substitution from stress to strain with a half in there. So just be aware that that half is floating around. If you're going to do these, some of the tute questions ask you to apply these techniques in Excel. Just remember that you've got a half floating in there you've got to account for in your calculations. Now, if we were to, instead of trying to rotate stresses or strains alone, if we wanted to go through the full compliance or stiffness matrix, we have to go through quite an involved process. So I'm going to write that up on the board. And I don't have notes to follow along with, so I may make a little mistake. So if anyone's got the notes open, just correct me if I stuff something up. Okay, so just some clarification before we go through this calculation. Notice here that I've got subscripts of 1, 2, and 6. And there's also 1, 2, and 6 in here. this is in the material axes. So this relates the stress and the strain in the material coordinate system. So when you see 1s and 2s in composites, they don't mean principal stresses, they mean material coordinate axes. Okay, so when you see stress 1, I don't mean principal stress, I mean stress along the fibre direction. When I say sigma 2, I don't mean second principal stress, I mean stress in the transverse direction. So for the sake of this calculation, I'm just going to call this thing Q0. The Q in the coordinate system of the material. The reason I use naught is because we tend to define the primary load axis as 0 degrees, and then anything from that we rotate around anti-clockwise through theta. So if I had a load, just a single load on a component, I would call this axis 0 degrees. If I rotated around 90, I'd call this axis 90 degrees. And I'm rotating anti-clockwise. So if I had fibres running at an angle like this, they would be 45-degree fibres. So we've got that we've got this situation where we've got a stiffness matrix for the material in its normal coordinate system, but what we really want is a stiffness matrix for the material in a general coordinate system. So we want this general one up here. And for general coordinates, we use x, y, and z. So any set of Cartesian coordinates, we've got sigma x, sigma y, and tau xy. Epsilon x, epsilon y, and gamma xy. So we can make some substitutions. We know we've got some things to substitute over here. Okay. Now, where's my 2 going to come in? I'm not sure I can do this in a simple way for you up here. No, I don't think I can do it in a simple way with matrix maths. You need to go through the full derivation. This is why I'm talking about whether I can do these calculations or not. I did say follow along in the notes because it's quite a lengthy derivation. Because you've got to get rid of 2's in here, you need some extra maths that's going to take up about 4 boards worth. But effectively what we end up with, which when you go to apply it in Excel is actually surprisingly easy to apply. You can transform from the material axes to any other angle by using a single matrix. So that matrix is this matrix here, which we call the transformed reduced stiffness matrix. Okay, so when I say transformed, it's been transformed through an angle, and it's a reduced stiffness matrix. And so this can be set up as an Excel calculation. You can set this matrix up with, you can calculate C and S, which are the same as our M and N. I don't know why I've changed. C equals M equals cos theta. S equals N equals sine theta. And I apologize, I think one of my textbooks used C and one used M and N. You transform between the initial terms which we've calculated. We've just calculated these. Okay, sorry, we've just calculated these ones here. These are just cosines and sines, and then this gives you the terms that go in there. So you can easily, it's tedious but not difficult is what I would define this calculation as. It's a long time to set up, but the actual steps are not tricky. You can transform between stress and strain in any coordinate system. Now I've basically set this as a tutorial question so you can have a go at setting it up in Excel. Now the reason this becomes important is because we don't make composites out of all 0-degree fibres. We make them in laminates where we have fibres at 45 degrees, fibres at minus 45 degrees, fibres at 90. And to work out the overall properties of that laminate, we need to have these Q terms defined. I've had a question about how to set up matrices in Excel, and I did do a very quick demonstration last week, but I realised that it's probably quite a beneficial thing for me to do it again. So I apologise, I'm going to have to do this kind of with my neck twisted because I am not duplicating these displays, I've only got what's up there. Okay, so any group of cells in Excel can be treated like an array or a matrix. So we can, for instance, if I wanted to say, I'll zoom this, hang on, I'll zoom this in. So if I wanted to create a stress tensor that was, say, 100 megapascals in 1, 50 megapascals and 25 megapascals in 6. So sigma 1 is 100, sigma 2 equals 50, and tau 6 equals 25. Then I can just set it up like that. If I wanted to make, say, one of these reduced stiffness terms, I could go 180, 181. What was the other term? I've rubbed it off. What was new one too? It was about 10 or something? 10? Oh no, new one two was 3, wasn't it? That was 10. That was 3. 0, 0. That was 7. 0, 0. Okay, so I've got a matrix there like that. Now, I haven't told Excel that that's a matrix yet. I can name it if I want. If I want to name it, I can highlight them and go up into this little box and call it Q. Okay, I don't have to do that. All the formulae will work regardless of whether I've done that or not. Okay. So say I wanted to calculate the strain. So if I said strain, now what I'm going to do is I'm going to highlight this one and call this one sigma or something, sig for strain. I can't put special characters in there, I have to use just normal text, so I'll come up with a name for it. So now these things appear, if you want to edit them later on, they appear in name manager. Okay. So when you click on name manager, these named arrays appear in here and you can go and edit them whenever you'd like. Okay, so if we wanted to calculate strain from stress and Q, we would have to strain equals Q inverse stress, okay, because I've got them on the wrong side. So I'll do that calculation. Where'd my mouse go? Sorry, I've got a... Okay, so to do a matrix formula, you have to select the cells you want to turn into the matrix formula, hit F2 to edit. So F2 just means you can type in a formula. Then I want to say equals M mults, because I'm multiplying two matrices together. Now I want the inverse of Q on the left-hand side. So I say M inverse Q. And I want sigma is what I'm multiplying it by. All right, and then to get the formula to go into the full vector, I have to hit Control-Shift-Enter rather than just Enter. Okay, so Control-Shift-Enter makes it a matrix formula rather than just a normal formula. And you'll see in the formula at the top, it gets these curly brackets around it. And the curly brackets means that it's an array formula, not a cell formula. Okay, so now this is all set up. So if I wanted to say now I've got 150 megapascals, I can see what happens to my strain. Okay, and I've got a unit irregularity here. These are meant to be gigapascals, and so my strain's in strange units at the moment. But remember, we've got to account for units. So if I wanted to fix the units, I can go in here and highlight them again, hit F2, and I know that I've done a unit error, so I can just fix that by multiplying by 0.001. Okay. So you can do any shape type of array you want in Excel, and rotations are easy enough too. You can put the transformation matrix in there, and it'll give you your rotation. So, okay. All right. So that's a rundown of how to do the tute questions in Excel. Okay, so we're going to look at laminates. So what I mean by a laminate is made from 2 or more plies of laminar. So each sheet we call a ply. Sorry, there's lots of terminology. I flick it around fairly loosely because I talk to people about composites all day. But a ply or a laminar is one sheet. The material comes in these thin sheets, it's sort of 0.1 of a millimetre, very thin stuff. And we make a composite laminate by stacking. So we put one down, and then we put one at a different angle, one at a different angle, one at a different angle, and we stack up what we call a laminate out of the sheets of material. And there's a reference angle chosen, which we talked about here, which we call 0 degrees. And that's how you tell someone, if you wanted to say to someone, I want this particular laminate, you start with the reference angle. So that's 0 is that angle. So if you tell them 45, the person making it knows that they have to rotate the ply 45 degrees relative to that reference angle. So there's a datum built into the laminate code. Okay, and every ply angle is given relative to that datum. Now, if I had a unidirectional material, and I can draw on this because I know I can rub it off. Okay, so say that's my 0 direction. What angles could I specify for angles of that ply? If I'm rotating it around, what angles could I go through? There's 360 degrees in a full rotation, but do I need the full 360 to specify? Okay, so I can go to minus 90 gets me to there. Plus 90 gets me to there, so I'm back to the same thing again. So I can I can specify anywhere from minus 90 round to 90. And typically, you'll use 90 instead of minus 90. So it's really not plus 90 round to minus 89.99, whatever. So you don't need the other angles because they just become if I was to say 0, 45, 90, if I went round to 135, I'm back to a minus 45 again. So it doesn't matter whether I'm that way or whether I'm that way, it's the same thing. So I only need from 90 to minus 90. And the way we denote the stack, so when we make this stack, we put something down first on the mold, so it's made on a metal mold generally, or sometimes a composite mold. And the first thing we put down is the first number we tell someone. So we say, put a 0 down. Okay, I'll put a 0 down. Then come along with another 0 and put it in the mold. Now I'll put a 45 in the mold. Put a minus 45 in the mold. So we stack up. We can tell someone a code for how to build the laminate. Now, if the mold is a strange shape, obviously those pieces are going to have to be cut from a roll in it to account for the fact that a 45-degree ply is going to fit into a mold in a different way than a 0 is. So you've got to cut the shapes at the particular angle on the roll of material. This stuff generally comes in rolls that are either a foot wide or a little bit over a foot wide and can be hundreds of meters long. So you've just got a big roll of this stuff and you just cut off pieces that lie in strips in the mold. Now, this would get pretty tedious. We don't want to write out that many characters generally when we're specifying a laminate, so we have simplifications. The first simplification is what we call blocking. So if there's lots of plies of the same thing together, we just put a subscript in. So if there's 2 zeros, we just write a 2 underneath. If there's 2 90s, we put a 2 underneath. The next thing we do is we group what we call balanced plies. So it turns out that the laminates perform best when you've got combinations of plies that are in what we call balanced orientation. So they're the same on one side of 0 as they are on the other. So a plus 45 and a minus 45, or a plus 30 and a minus 30. So those are what we call balanced. And we block them together with a plus minus or a minus plus sign. So you can see now we've saved ourselves a bit of handwriting. We had this initially. We've now got this. So we've already shrunk down our laminate code quite a bit. The next thing we can do is apply symmetry. So this is our initial laminate code here. If you notice that it's symmetric about some plane in the middle. And we can cut it there and just write the first half with an S after it. So we've got 2 zeros, a plus minus 45, a 90, and then we mirror that again. So that's what the S stands for. And we can combine all those different things. So here we've got 0, 90, 0, 90, 90, 0, 90, 0. So we've got a 090, we've got two of them, 090, 090, so there's a 2, and then it's symmetric, so we've got an S. So we can combine all the rules into one thing. And the last complication is this little bar here. Often if you've got an odd number of plies, the middle ply will be symmetric about sort of half of that ply. So we put a bar here. If I could somehow cut this 90 in half, I would have a symmetric laminate either side. So I put a bar over that 90 to designate that it's the middle one in an odd number of plies. So with this set of rules, you can look at any laminate code in any textbook and understand what someone means. So anytime anyone specifies a laminate, you can look. It's very rare that you'll see them published for real structures because it's commercial information. But if you look in any notes on making composites, you'll be able to understand what they mean by their laminate designation. Fabrics are one thing that complicates it slightly. So a woven fabric just like what you're wearing in your clothes, has fibres woven together in a grid. So there's fibres this way and fibres this way. So we now don't need 0 to 90, we need 0 to 45. Okay, and so 0, because a 45 and a minus 45 are the same thing. Okay, or so minus 45 to plus 45 we need. So we go anywhere from there around to there, and we can write the fabric codes out in the same way. Okay. Often you'll see, instead of just a plain 45 for fabrics, people will write a plus minus 45. And these on their own don't mean anything. You'll often see T300, SciComm 970, plain weave, and then a laminate code. So you have all that you need to interpret how the material is made. So T300 tells you it's a T300 fibre. SciComm 970 tells you it's a SciComm 970 resin. Plain weave means it's a fabric. And then the laminate code tells you the order that it's made. So you can go through the full designation. You can read any textbook on composites now and you'll be able to understand at least what they're talking about when they talk about the laminates. Okay. So, three things that will pop up a lot in composites textbooks and in composites notes are these three terms. And so we'll go through them carefully. I've already described what one of them is. A balanced laminate is a laminate that has the same number of plus degree angles as minus degree angles. So if it's got 1 plus 30, it has the equivalent minus 30. If it has a plus 60, it has a minus 60. So there's a pair. Every ply that's not 0 has a pair in the laminate. Symmetric means that somewhere in the middle of my stack I can mirror it and see the same thing the other way around. So if we can put a little S at the end of our laminate formula, means that we've put some plies down and we could do exactly the same thing in the other half. Quasi-isotropic is, we know isotropic means looking the same in every direction. Well, we can never get that for composites because they're different in plane than they are in the through thickness direction. But quasi-isotropic means it's nearly isotropic. And what that means is that there's plies in an even spread of directions, so that if we were to test this material just in plane, it would look like an isotropic material. We could do a test this way, we could do a test this way, we could do a test at 45 or at any angle, and we would see very similar properties. So quasi-isotropic means, for all intents and purposes, it behaves like an isotropic material. And that was how most composites design was done for a long time. They made what was called black aluminium. They just made composites in a quasi-isotropic fashion and bolted it onto the aircraft in the same way as they did with aluminium. And it still gave some advantages, but it was not using the complete tailorability of composites. So it was lacking some of the efficiency that you could gain from having tailored materials. Okay, so we have one topic that's quite important that I have to kind of scoot through, unfortunately, which is classical laminate theory. So we know now how to get properties from, actually I'll use this board. Okay, so what we're really after when we characterize materials is we're after engineering properties. So we're after things like E, G, and U that tell us, and stiffnesses and strengths. So sigma, max, ultimate. We're after the ability to determine how much something is going to deflect for a certain amount of force, or how much it's going to shear or skew is the correct term for a given amount of shear stress, the amount it's going to shrink transversely. So these engineering properties are the things we really want. And we now know how to go from what I call constituents. So the fibre and resin. We now know how to go from constituents to apply. This is often called a lamina. Note the particular ending, lamina, means singular. It's a singular. It's out of a. It's not a laminate. Now we can do that using rule of mixtures. Those formulae we had earlier. Now, to go from apply to a laminate, we use classical laminate theory, which is what we're going to cover now. So we know how to calculate the stiffness, so things like E1, E2, Q11, Q22, all these things. We know how to calculate them based on the constituents. Now we want to know how to calculate the same things for a laminate that's made up of multiple different plies. So there's a bunch of assumptions, and I'll put them all up, and it's not necessary to go through all of them, but all I will say is that for most thin-walled problems, so most aircraft structures are what we call thin-walled problems, all these assumptions hold, and so we can get away with using classical laminate theory fairly confidently for thin-walled problems. So you can keep these for reference, but they're not necessarily that important for the analysis. So how are we going to work out, how are we going to start classical laminate theory? What did we do before? Well, we considered what would happen if we had a bar of composite material and we pulled on it with a particular stress. We measured the strain that it would deform by. In reality, what we actually did, is, which is a little bit more accurate, is we applied a force and we measured a deflection. And using the rest of the properties which we know, the initial geometry, the length and the area, we calculated the modulus. So the first point in working out any stiffness is not stresses and strains, it's actually forces and deflections. And so this is the basis that classical laminate theory starts with. So we take a little piece of material, like this material here. Okay, we've got an X, Y, Z marked on that material. And we'll take a little slice that's oriented in the XZ plane. So this little slice here. Now, the deflections at any point in that plane are a function of X and Y. So as you go across the plane, the X displacement, which remember is U, and the Y displacement, which is V, are a function of position. So if we're here, we've got a different displacement to here. That's not that tricky. So all we know is that the displacements are a function of the position. Now, if we were to bend this material, then we can work out the displacements. The displacements get smaller or bigger depending on where you are in the thickness. So if you started here at B and you were bent, your position is slightly less than the midplane of the lamina, or your deflection is slightly less. So if you can read the subscripts, I don't know if you can, UB is slightly smaller than U naught. So this is U naught and this is UB. Okay, because there's been if it's bent, there's a change in angle of a plane. So that's where we get these formula from. So the displacement at anywhere through the thickness is a function of the displacement at the midplane minus some rotation component. And we can write that out more generally, that the displacement at any point is the displacement at the midplane minus the angle times the position in the through the thickness. Okay. Now, the next thing we did in this calculation is we worked out that strain equals the extension over the length. The equivalent here, this is also equivalent to d extension dx. I don't know what units I should be using there, but strain is the derivative of displacement. All right. So to work out what the strains are, so here we went extensions to strains, and then we could calculate stresses, and from that we could calculate forces, or we could do it in other combinations if we wanted. We're going from extensions to strains here on this slide at the top. So we take the derivative of strain with respect to, this is du dx. We can do the same in the y direction. And we can do the same in the shear direction. Now, we'll break these up. Each of these terms has a term with v naught and a term with d2w dy squared, and so we can separate them out. And we call the constant bit the strain strain naught, and the other bit's kappa. So we can write a matrix like this here that says the strain at any point in x, y, and shear is the strain at the midplane of the laminate plus z times the curvatures. And these curvatures are just like you would think of curvatures from mathematics. They're the second derivative of the z position. So d2w dx squared or d2w dy squared. They're exactly, if you asked what the curvature of a parabola was, for instance, you would take the second derivative of the function to get to the curvature. It's exactly the same here. These are second derivatives of the position. So we now have completed this step. We've taken our the derivative of strain of displacements to get to strains. Now, if we look down here at the bottom of the slide, strain in a composite laminate and stress, the modulus of all the different plies is different. So we have to relate strain to stress, and we do that through this Q matrix, which we're already familiar with. So we've already got to this point in one of the previous slides. So if we substitute this into here, then we can sort of expand our equation a little bit more. And again, I urge you to not freak out about the number of terms in these matrices. It's the logic that's more important here. So for any ply, which we give a subscript k, so for any layer, we can define the stress in that layer here, stress k, as a function of the strain at the midplane. So the strain at the midplane plus something to do with the curvature, so how much it's bending. And we can add up, just like we could say F equals sigma A. Now, this area is a sum of, if I had a composite that I cut, so what I'm showing now is if I took a bar that I had a force on and I cut it, and I looked at the cut, I would have ply 1, ply 2, ply 3. I would have all these plies. Now, we can sum up the stresses on each one of those plies, or we can sum up the areas of those plies to get to here. So if I wanted to work out the force on the total stack, I could do that by, if I had the stress in the area of each level, I could add up to the total force. So we have here forces. This N is a force per width. So because we don't know how big our cell is, we could have this cell half as big or twice as big. But we want force per width. We don't want force on its own. To do that, we integrate stress through the thickness, and we get this relationship. And when you blow it up, it looks like this. It's getting seemingly more and more complicated. But it does reduce down to something a lot simpler in a minute, and we'll see that. Moments is the same. If you wanted to know the bending moment, you could sum up the stresses times the moment arm times the the thickness. That gets you to moment per unit width. This is moment per width. G equals force times distance over width. So this has units of force. Can we see that these formulae are looking quite similar? And turns out that the combination looks like this. If we put together, this is forces and moments, and this is strains. Now in the middle here, we have something that's like a stiffness matrix. It's not quite a stiffness matrix yet, but it's something like a stiffness matrix. So with our bar, we had stress equals E strain, or if we did it with matrices, actually no, sorry, that's C. Okay. Now, we haven't, what I'm showing on the board there isn't quite this. What we've actually got is, we've sort of got forces related to strains. So it's not quite a stiffness matrix, but it's similar to a stiffness matrix. So the way to read this matrix, and we'll look at calculating the terms in a second, the way to read this matrix is AXX relates the force in the x direction to the strain in the x direction. So that's just like what you'd think of as a Young's modulus. So it's not exactly the same as Young's modulus, but if something has a high AXX, you have to put, for the same strain, you get a higher force. So it's a stiffer laminate. And AYY is the same in the y direction, so and ASS is like a shear modulus because it relates the shear force per unit width to the shear strain. So these four terms there and that term there are what you'd expect with a normal isotropic material. You could construct one of these for steel if you wanted to. Normal materials also, you can have these four terms, dxx, dyyy, dyx, and dss, or those five, sorry. And what they relate is moments to curvatures. So if you bent a beam and put a curvature on it, moment equals minus EI d2w dx squared. Okay, so for any isotropic material, the moment and the curvature are related to each other. So that's what we've got in the lower right-hand corner here. So for isotropic materials, we would only have a very sparsely populated set of terms here. The rest are what are exotic. They're only things that happen in orthotropic or anisotropic laminated materials. And they give the composites can have very, very strange properties. So let's imagine that there's something in I'll get a different color. Let's imagine that there's something in this box here. Okay, and what that box tells me is that if I put a shear strain on the laminate, I will get a force in the x direction. So what that means is that I can construct a composite where if I shear it like this, if I try and apply a shear force to it, it'll actually pull my hands in and out in the x direction. So normal materials don't do that. There's no equivalent to this in isotropic materials. Now if I get another colour and I look at, say, let's look at this term here, okay? So what this term is telling me is that if I apply a curvature in the x direction, I'll get a force in the x direction. So if I bend it, which would normally just create a bending moment, it actually is creating forces that are extensional as well. And the inverse is true. If I pull on it, it'll bend. So unlike a normal material, if you pull on it, it just gets bigger. If you pull on a composite that's not stacked, that's stacked so that those terms are non-zero, it'll bend. So you can get coupling between all sorts of different modes. You can have a composite where you pull on it and it warps, pull on it and it bends, pull on it and it twists. Like there's a full set of coupling. Instead of them being completely decoupled like a normal material, you can create a laminate that really does whatever you want it to. You can make something that as you curve it, it pushes in and out. So there's all sorts of strange things that can be done. Now, from a design perspective, most of the time we don't want that because it makes the materials very, very hard to handle on an airframe. So luckily there's some things that we can do to get rid of those terms. So what we're trying to do is we're trying to get rid of this box, make that all zero, trying to make this all zero, and we're trying to make these terms here zero as well. So that we turn our laminate back into what I'd call a normal material, a material that's not coupled between extensions and bending and extensions and twisting. Now the way we do that is if we use a symmetric laminate. If we have a symmetric laminate, all the B terms go to zero. Okay, because you'll see from the calculating the B terms a couple of slides ago, which we'll hopefully revisit in a couple of seconds, all those terms go to zero if the laminate's symmetric. And these terms, to get rid of them, we need a balanced laminate. Okay. So if we make a laminate that's both symmetric and balanced, it returns to what I would call a normal material. There's no coupling between the different extension and bending and extension and shear and all those things. So that's why I introduced those terms, symmetric and balanced, because they are very important for most laminates. We don't want them to have those exotic kind of behaviors. Okay, so to calculate these terms, we have to go through this process. It's helpful to have a bit of a recap of what these terms relate to. So this term here relates our stress in the one direction to our strain in the one direction. So it's the big term because it's the one that's carrying it's got all the fibres carrying the load. So the stress in the fibre direction is the strain in the fibre direction times this very big number, okay, plus a smaller term depending on the strain in the other direction. So the big one, the one that's contributing most to the stiffness, is the fibre term. And this term is relating the stress in the two direction to the strain in the two direction. So it's small because when we load in the two direction, we're loading mainly matrix. We're not loading the fibres in their strong direction. So the relative magnitudes of these terms are dependent on what we're actually doing to the different phases of the composite. So if we wanted to have a quick way of rotating this around by 90 degrees, instead of going through the transformation matrix like we did last week, there was a way that you could get Q in any coordinate system. Q theta equals T theta times Q naught. Okay, you could do any kind of transformation. We're not going to worry about transformation matrices because they're cumbersome and tricky to do in class. What we're going to do is do a quick cheat transformation, and the one that we can do without even thinking is 90. Now let's think about this. If we wanted to work out the Q in the 90-degree direction, what we've done, we had a coordinate system that was 1 and 2 like this. Now, if we wanted to get Q in the 90, so we wanted to work out this case, then all we're really doing is switching our 1 and 2 indices around. And it turns out that we can just do that to get the Q for the 90-degree direction. We can just switch anywhere where there was a 1, turn it into a 2, and leave everything else alone. So for the special case of making a 90-degree rotation, we can just switch our coordinate axes around. So the only thing that changes is that the 1, 1 goes into the 2, 2 position, and the 2, 2 goes into the 1, 1 position, because 1, 2 stays the same and 1, 2 stays the same. Okay. Because remember last week we showed that Q12 equals Q21. Okay, those two things are one and the same. Okay, so armed with this knowledge, we're going to make a simple laminate. Okay, and this laminate's going to be called a cross-ply laminate. So a cross-ply laminate just means that we've got fibres, one layer of fibres like this, the next layer of fibres at 90 degrees, the next layer of fibres at 0, or some combination of that. So the fibre layers that we put down are just perpendicular to one another. Okay? So there's no other special orientations. We're just putting perpendicular fibres down. So the particular cross-ply laminate that we're going to look at is a simple one. (090S). So you should know from the code last week, and if you've had a go at the adaptive tutorial, and I know someone's pointed out that there's a bug in one of the tutorials, but not this one, that's the code that, well, that's the expansion of the code that I'm showing there. So it's a 0, 2 90s, and a 0. So if we looked at that as a stack, what we're going to assume for this particular problem is that the thickness of each ply, which I'll give a subscript for the moment, T ply, is 0.15 millimeters. Now let's look at that side on. So now we've made our laminate. How thick would this laminate be? 0.6 millimeters, yeah, because we've got four copies of our 0.15 millimeters. Okay, so the whole thing's 0.6. So the half thickness is 0.3, okay? And the mid-plane's, the neutral axis is in the middle, or the mid-plane. Now if we look a little bit closer and we try and break it down by plies, I'm going to say there's a 0 on the outside, on both sides, and there's a bunch of 90s in the middle. Okay, so I haven't drawn that particularly to scale, but this is 0.15, that's 0.3, and that's 0.15. And the reason I've collapsed the two 90s in the middle into one layer is because elastically they're the same. I mean, if you look at these under a microscope, they're thousands of little fibres stacked together, and the fibres really don't know where one ply starts and the next ply finishes. If they're all in the same orientation, they're behaving as if they're just one big ply. So for the sake of our elasticity calculations, we just treat the two 90s that are in the middle as one big block, and it saves us some maths. Okay, so let's work out how to calculate these matrices. We'll have a closer look at this formula up here. So, this Aij here, remembering that A is actually a matrix. So I've collapsed it here into one term, but it's actually this whole big thing here. Okay, so Aij is actually a 3 by 3 matrix with A11, XX, AYY, XY, sorry, I'll rub that out. I'll do this where I've got a bit of space down here. AXX, AXY, AXS, AYX, AYY, AYS, etc. Like, so it's a 3 by 3 matrix. Okay. Now we can calculate each term of that independently using the formulas on this page. Now, we know what this bit is, okay, because we can just sample that from our Q matrices up there. The Z's are the positions of each ply. So if we look closely at this case here, we're going to number this ply 1, this 2, and this 3. And then what we're really interested in this calculation is the edges between the different levels. So we call this Z0, Z1, Z2, and Z3. So they're where one ply stops or starts and the next one finishes, vice versa. So we're starting a ply here, finishing it there. Next ply starts and finishes. In some sets of notes, these are written as H0, H1, H2, H3. That's just depending on where the notes have come from. H and Z are the same thing. Okay, so let's put values to these. If we wanted, they're all measured relative to the midplane. So Z0 equals minus 0.3 millimeters. So we start at the midplane and we've gone downwards 3 millimeters. So what would Z1 be then? 0.15 millimeters. Z2, 0.15 millimeters, and 0.3 millimeters. Okay, so we're just giving ourselves datums to do our calculations with. So we'll keep that up high and we'll start our calculation. So AXX equals the sum, sorry, that's not the sum symbol, that's just a bracket, sum of K equals 1 to N of QXX. So if there's an if there's an IJ on the left, you sub in the same IJ on the right. So here's XX and here's XX. ZK minus ZK minus 1. Okay, let's have a think about what it looks like a fairly complicated thing, but all this is just the thickness of each ply. Okay, so Z1 minus Z0 is just the thickness of each ply. So let's write it out longhand now with all the k's substituted in. So k equals 1, we get QXX of our first ply times 0.15 plus QXX of our second ply times 0.3 plus QXX of our third ply times 0.15. Now, referencing this picture up here, what is QXX of our first ply?
182.
Yeah. Remembering that there's a 10 to the 3 hanging around there. So 182 E3. I'll write in this notation, that just means 10 to the 182 E3 times 0.15. What's QXX of our second ply? Yeah, so this is the XX position for our first ply. This is the XX for our second ply, because we've got a 0, then a 90, and then a 0. So we have one of these, then one of these, and then one of those again. Okay, so let's cram that through a calculator. That's a good question. What's the units of this? Okay, let's have a look at how we use them. Remember? Okay, so we've got, up here we've got force per unit width. So this is newtons per millimetre. Here we've got strain, which is dimensionless. So the units of A have to be the same as the units on the left-hand side. So it's newtons per millimetre. So we had a megapascals times a millimetre, megapascals times a millimetre, megapascals times a millimetre. So the units that come out here are newtons per millimetre. So just as a rough guess of what's going to come out here, I'm thinking 60 by 10 to the 3 approximately. Yeah. Okay. And just because this one's not going to make much of a contribution, that third of that's about 60. Okay, so 55 by 10 to the 3 newtons per millimetre. Now you'll notice here that this term was pretty big. This term is pretty small, it doesn't have much of a contribution. And this term's pretty big. It's because when we load in the 0 direction up there, in the XX direction, the zeros are doing a lot of work for us, but the 90s aren't. The 90s we're loading transversely, so they're not adding much to the stiffness. Okay. So we'll do one more of these quickly. And I'll just write it out in longhand straight away. AYY equals QYY of our first ply times 0.15 plus QYY of our second ply times 0.3 plus QYY of our third ply times 0.15. So what are the QYY values we're sticking in? Where's QYY? Well, QYY for our zeros is this one here. QYY for our 90s is this one here. So we've got 2.5 E3 plus 182 plus 2.5. So without having to resort to crowdsourcing, I can tell you what the answer is going to be. Okay. But if we look closer, even though the answer is the same, it's coming from a different place. Our first term here now is small, our second term's big, and our third term's small. And that's because YY relates the stress in the Y direction to the strain in the Y direction, or the force in the Y direction to the strain in the Y direction. So that's loading the 90 fibres, not the 0 fibres. So the big stiffness component is coming from the 90s and not from the zeros. Okay, and the others you can go through in exactly the same way. A, X, Y, you just have to sub in QXYs, and A, R, S, S, you sub in QSS. Okay. Now for this particular case, the ones that are missing, AXS, AYS, those ones are missing because we've got zeros up here. We've got 0 there, 0 there, 0 there, 0 there. So when we do the sum, all these coefficients, 0, 0, 0, the whole thing ends up being 0. The only reason they're missing is because of the particular angles of fibre that we've chosen. We've chosen 0s and 90s. If we'd added some 45s in there, this whole matrix becomes populated. So these other terms don't immediately go to 0. You actually have to calculate them. But once you've got this set up in Excel or MATLAB or however you want to set it up, those terms get automatically calculated. You don't have to sit there and manually do it. And in exams, I would not ask you to do the transformation, but I may ask you to, if I've given you these beforehand, calculate one of these terms. Okay. So in practice, what this tells us is it tells us the A matrix tells us the magnitude of the in-plane stiffness. So with normal materials, if we've got a modulus like E, we can work out there's no difference between the in-plane and the bending stiffness, really. The in-plane modulus is determined by the Young's modulus, and the bending stiffness in part is determined by the Young's modulus as well. The only other factor that comes in is the thickness. So materials that are thick have higher bending stiffness than materials that are thin, because there's instead of just E, there's in all the equations there's an EI, and EI is a geometry term. Okay, so anything to do with bending has an EI. Anything to do with in-plane loading just has an E. Now with composites, what the A matrix is, it's the equivalent of this in-plane modulus. It's telling us for how, if we pull on a laminate in plane, how much strain we're going to need, or if we strain a laminate in plane, how much force we're going to get. So we can use these matrices either way. So it's useful for telling us if you've got a thin-walled structure and we want to know how stiff it is, it's very useful for that. What it doesn't tell us is how they behave if we put local bending on them. So what we need is this D matrix, which is this one. Now if you'll notice in the D matrix, the formula is fairly similar. On the left we've got this IJ subscript again, which is mirrored in here. The main difference is that instead of this being Z minus ZK minus 1, we've got Z cubed minus ZK minus 1 cubed. And there's a different constant out the front. Now, the effect that that has is that it amplifies things that are away from the neutral axis. So if we look at if we had something that was like we've got up there at 0.3, 0.15, 0, minus 0.15, and minus 0.3. And I'm just going to say Z, in this case it'll be 4. So we've got 0, 1, 2, 3, 4. Z4 minus Z3 is just the thickness. Okay. And it's the same. Z3 minus Z2 is also 0.15. Z2 minus Z1 is also 0.15. All the thicknesses of each ply are the same. So the contribution of them to the in-plane stiffness is constant. But in bending, we have to amplify the things that are away from the center. Just like when you make an I-beam, the material at the top and bottom of the I-beam has a bigger contribution to the second moment of area. With a composite laminate, the plies that are on the outside have a bigger contribution to the bending stiffness than the plies near the middle, because they're experiencing more strain as we curve the laminate. So what happens when we calculate the cubed terms? Z4 cubed minus Z3 cubed, okay, 0.3 cubed minus 0.15 cubed. So I want you to calculate those two terms. 0.3 cubed minus 0.15 cubed, or 0.15 cubed minus 0. And you'll see that this term is actually significantly bigger than this one. Even though the gap between the two numbers is the same, because we're cubing it, we're amplifying the magnitude the further we are away from the neutral axis. Now you go through the maths in exactly the same way. So the maths is exactly the same. dxx equals qxx 0 or qxx1. But now we have to have 0.3 cubed minus 0.15 cubed on 3 plus, plus, plus. So there's no change to the maths other than the terms we substitute in. But the effect that it'll have in this case is that AXX equals AYY, but DXX does not equal DYY. Because there's zeros on the outside and 90s in the middle. So if we bend it around, if we put a bending moment on the X face, it'll be much stiffer than we put a bending moment on the Y face. So I'd ask you to go and have a go at that calculation yourself. But the effect that this has is that we can actually, because these two things are decoupled, we can make laminates that have very different in-plane behavior than they do bending behavior. The other question I'll set for you as a thought experiment, and maybe a kind of another tutorial question, is I haven't really touched on this B matrix. Okay, I've kind of ignored the B matrix. Now, last week I said that the B matrix would go to 0 if we use symmetric laminates. Okay? What I want you to convince yourself of is that that term will actually go to 0 if the laminate's symmetric. So you can calculate it for this case, which is a symmetric laminate, and you should see that it'll equal 0, or very close to it at least. And I want you to convince yourself that that's true for the general case as well. So what I want to do is just do a quick example to show you how we use these from an engineering perspective. Because at the moment we don't really have what I would call an engineering constant. We've got more of a laminate constant. We need to be able to use this in an engineering sense. So now that I've rubbed it off, I'm just going to have to redraw it again, sorry, quickly. So let's say we took a little piece of our 090 laminate, a very simple cross-ply laminate, and we made a bar out of it. So that we're looking down on the laminate now, and the width of that we'll call B. And for argument's sake, we'll call the length of it L. Now, if I wanted to work out what I'd call a modulus for this material, like Young's modulus, how would we do it? So let me see if I can find the right term here. Okay, remember if this was a bar of metal, we would say that stress is equal to E strain, and we can kind of make an analogy to that for composites. We can say that the stress in the x direction is this is an effective property, an effective modulus times the strain in the x direction. Because if we know that modulus, it makes we can apply the same sort of mass that we would use for metals to composites. Now, how did we measure the modulus of a metal bar? Remember I asked this sort of from a fundamental perspective. We stretch it, or we apply a force to it, and we either stretch it and measure the force that it takes, or we apply a force and we measure the stretch. Okay, so for E, is really the force that we apply over the cross-sectional area divided by the extension over the initial length. Okay, so that's just stress over strain. Now we can do the same thing for our laminate, but we just have to be a bit cleverer about what we sub in here. Now, if we're substituting in things from our A matrix, what's the force that we have, assuming we're doing this, so we're measuring E over L, we can just change back to strain. Okay, because we have strain in our calculation here. Okay. Now, what's the force that we have to apply? I just go back to this case here. Actually, what I want, sorry. So I'll just take one little sidetrack before we answer this question. We can invert these matrices too. So I've done it, it's in the notes, and I did flick through it quickly last week, but we can do an inverse of the A and B matrix to get little a's and little b's. And instead of having forces on one side, we've now got strains and forces on the other side. Okay. So if we apply the strain, we can measure the force, or if we apply the force, we can measure the strain. Let's assume we've applied the force, because that's the easiest thing for us to do in a test. If we apply the force, we've got nxx times b is the force that we're applying. Okay, this is force in the x direction per unit width, and this is the width. And the area that we have here, the cross-sectional area, equals B times the thickness of the laminate. So if we rearrange, if we substitute some things in here, we get NXX B on B times T times strain, XX. But if we look up here, what we've actually we can show is that the strain in the X direction is just AXX times the force in the X direction. So we can make a substitution in here. So now we've got an effective modulus for the laminate. So we can also do this for bending as well, and I'll do. There's a tutorial question where you're asked to do this, I believe. If there's not, I'll put one up. In bending calculations, bending moment is minus EI times d2w dy squared. So this is minus the bending stiffness times the modulus, or sorry, times the curvature. So if we're going to do this with composites, we need to have an effective EI as well. Okay, because EI is not defined, we don't know this for our composites in general. We need to work out an effective version. All right, and I can tell you now that it will be a function of dxx, because remember A is the in-plane modulus, and D is the bending. Okay. All right, so we'll leave that for the moment. Let me just think about what I can... I'll go through this quickly. This is fairly comprehensively covered in the notes, but I'll go through the bits that are going to cause us problems. Composites fail in a fairly complex manner. Unlike metals, which are fairly easy to predict the failure of, composites have they can fail in the fibres, they can fail in the resin, they can fail at the interface between the two, and they also will fail in a different way depending on whether you load them in compression or whether you pull them in tension. So all of these things contribute to the strength of a composite. When someone asks you how strong is a composite, if someone asks you that question with a metal, how strong is a piece of steel, well, the first thing you would go back to is you'd probably think about a critical stress, an ultimate stress, or a yield stress. You'd say 500 megapascals. And for an engineering, if you're talking to an engineer, they'll understand that the total force that a piece of steel can carry will depend on the amount that you put in there. So there's a cross-sectional area, but the property that defines the underlying strength of the material is a stress, a critical stress. With composites, it's a little bit trickier to do that because they're made from stacks of different orientations. There's all sorts of complexities to them, so it's very hard to define what the critical stress for a composite is. And in fact, in most cases, there's probably multiple critical stresses depending on whether we're loading the matrix, whether we're loading the fibres, tension, compression. So there's lots of complications. So when someone says how strong is a composite, it's actually a kind of silly question. You can't answer that very easily. What we can do is we can predict failure of composites using a theory of failure in the same way as we predict failure of metals using a von Mises theory of failure, for instance. And the reason I was quite specific about our theory of failure in the solid mechanics class is that it's very important when you come to composites because theories of failure are many and they're all not very good, but they're the best that we have at the moment. And this is all covered in the notes, so I'm not going to cover this in too much detail. But basically, as I've said, they can fail in different ways if you load them in tension. If you load them in compression, you'll see different things, micro-buckling and kinking, fibre shear. If you load the matrix in tension, you'll get cracking in the matrix. If you load the matrix in compression, you'll get a compressive crack in the matrix, and this sort of looks like the compressive crack in concrete or something like that. Shear failures, delamination where the plies themselves actually break apart. So there's lots of complicating factors here. And we need to predict failure using a theory of failure. So what I've set up here is a failure criteria. Okay, you can interpret that as a theory of failure. So with metals, one of our most common theories of failure is von Mises theory. There's also maximum principal stress theory for brittle metals. With composites, those failure criteria are not a small set. There's a very, very large set. You'll hear things like Psi-Wu, Psi-Hill, Hashin, maximum stress, maximum strain, strain invariant failure theory. And the further you dig into this, there's lots and lots and lots and lots of failure theories, and there's a few summarised in the notes. They all depend on different things, and we'll see that there's a real challenge in predicting the failure of composites. The reason that there's such a challenge is because we have to define what we call allowables. We have to do a test to determine how strong something is in the test condition, and then generalize that small number of tests to all the different load conditions that our composite might see. Just like when if you wanted to make a pressure vessel, like in the tute question, you have to test the strength of a bar of steel. Then if you go and make a steel pressure vessel, you've got a von Mises failure theory to work out what kind of pressure you can put inside before your tank will yield. It's the same with composites. We have to do a small number of tests to determine the allowables and then generalize that to a more complex loading condition. Okay. So these are some, a list of some very small number of the failure theories that are around. Maximum stress, maximum strain, Psi-Wu, Psi-Hill, Hashin, SIFT, okay, strain invariant failure theory. They all work in slightly different ways. They're often plotted like this, and if you went back to the solid mechanics notes, you'd see the same thing for a von Mises failure. So a von Mises failure envelope for a piece of metal might look like this, where you've got stress in the one direction or whatever direction you're testing and stress in the other direction. In this case it's principles, but it can also be in the fibre coordinates. And with composites we can do the same thing. We can test it in the fibre direction in tension and work out a strength. We can test it in the fibre direction in compression and work out a strength. Matrix direction in tension and work out a strength. Matrix in compression and work out a strength. And then the simplest failure theory is just to put a box around those and say, if we're inside this box, we're safe. If we're outside the box, it's going to fail. Turns out it doesn't work very well, but it's a simple, rough and ready way of working out whether a composite's going to fail. The next most complicated thing is to do a Psi-Hill type formula where we combine them all into one ellipse. And when you plot that out, it ends up looking something like the von Mises failure ellipse. In fact, Psi-Wu and Psi-Hill are both derivations of von Mises failure theory for composites. Okay, so this is the Psi-Wu failure ellipse. Okay, these don't work very well because they actually relate the tensile properties to the compressive properties. And there's a very famous paper by an agitator called, he's a grumpy old bugger, but he writes interesting papers and likes to stir people, called John Hart Smith, who is from the US and worked for a number of years for Boeing, but now is in Melbourne. He showed that these failure theories are all a load of rubbish because theoretically, according to them, if you weaken the tensile strength of the composite, you'll strengthen the compressive strength, which is obviously rubbish. So he wrote a paper called Improved Submarine Materials, or Improved Material for Submarine Hulls by Decreasing the Tension Strength, just to show that it's kind of rubbish to say that if you just push this ellipse around a little bit, if you weaken this, you can strengthen this, which is nonsense. A submarine hull, for those people who are wondering, is really the opposite of an aircraft fuselage. So instead of the pressure inside being high and the pressure outside being low, a submarine hull is the opposite. The pressure outside's high and the pressure inside's low. And so they're just loaded in biaxial compression instead of biaxial tension. It's an inverse pressure vessel. So then you can go more and more complex, and you'll see in the tutorial questions that you can dive further and further and further into this failure theory argument. And for anyone who's picked composites as their research topic, you will have noticed that lots and lots of work is still being done on predicting failure of composites. We are actively engaged with Boeing and have been for a number of years now to try and improve failure prediction with this technique called strain invariant failure theory, which they now call Boeing onset theory. But if you look up Boeing onset theory or strain invariant failure theory, you'll see my name pop up a couple of times. There's not too many papers out there at the moment, but we've been working for a few years trying to improve prediction, because it's big money predicting the strength of things, because if you can't predict the strength of things, you have to derive all your information from test data. So you make a component, you test it, and you go, okay, that passes whatever criteria we set. Then you make a bigger component, and all of a sudden, what you thought the load that the component could take, it can't take that load. So you've then got to go back to the drawing board, redesign it, rebuild prototypes, and go through the design phase again. And what can happen is what happened to the 787, where you get right to the end of the design and you've got a whole aircraft there, and you load that aircraft in a big fixture to test its ultimate wing load capacity and find cracking in the wing root. And then everyone freaks out and realizes that we have a multi-billion-dollar problem on our hands and have to go back to the drawing board and redesign whole components for the aircraft. So if you've got a better predictive capability, if you've got something that in a computer or on paper predicts failure more accurately, then you can save yourself very big dollars from a design phase later on down the track.